So we're going to discuss some basic properties of the Schrodinger equation. So let's write the Schrodinger equation first. So it's I h bar del psi by del t is equal to minus h squared by 2m Laplacian of psi plus v of psi. So the first thing to notice is that it is linear. There is no psi squared in it. So which means that if psi 1 and psi 2 are both solutions, then any complex linear combination, say psi 1 a psi 1 plus b, psi 2, is also a solution. So why complex? Because the Schrodinger equation is a complex equation. It has I in it explicitly. And we saw that psi has to be complex. In certain cases, it may not need to be complex, but in general, psi is complex. So, the domain of solution will be over the complex numbers. So this is property number 1. It is linear. It's a very important property and a very nice property. Well, the second property is that it's complex, as we have already discussed. And it is necessarily so, otherwise we would not be able to satisfy the energy conditions that were proposed by as a consequence of the de Broglie relationship, right? And so, for example, some of the even simpler solutions, for example, the plane wave solution is complex. So this is something very important. And it's actually related to what I'm going to say next, that it's not discussed enough. It's a time reversible equation. So in many quantum processes, if you look at the interaction between two particles, or more than two quantum particles, and if you, suppose you're taking a movie of it, and suppose now we turn the movie backwards, and you say, is that also seen in the natural world? The time reverse process, is that also described by the same physics? And it turns out that in most of the cases, it is true. So the Schrodinger equation is a time reversible equation. And how we can see that? It's a bit subtle. So the Schrodinger equation has I h bar d by d tau psi. And on the right hand side, we have h squared by 2m, this thing. Now the thing is that if we take t to minus t, which is how we reverse time, then the left-hand side picks up a minus sign. Of course, this is no longer the Schrodinger equation, but now if we take the complex conjugate of this equation, then psi becomes psi star, and then I becomes minus I, so we go back to this plus sign here, then we see that psi star also satisfies the Schrodinger equation if psi does. And it turns out that psi star is the quantity which describes the time reverse process. And we're not coupling our particle to an electric field or something like that. Here we are not considering a charged particle, but if you were to consider a charged particle, what we would see is that, time reversing it and taking the complex conjugation also reverses the charge of the particle. In other words, it turns a particle into an antiparticle. Anyway, that's outside the scope of this course. So these are some of the main properties that I wanted to discuss about the Schrodinger wave equation.